In this video, we will talk about the ANOVA or analysis of variance for simple linear regression. ANOVA or analysis of variance, is a procedure that is used to evaluate for the quality of the estimated regression model. In fact, analysis of variance is a tool that is used to analyze the statistical data in a general way, but it is also used for the regression as well. So we will talk about the special case of ANOVA for the linear regression. So ANOVA just divides the total variation. Remember, it was SST, which is yi minus the y bar. This is the total variation into two meaningful components. Okay, and what was them? It was SSR, the regression sum of squares yi hat minus y bar, the variation due to the regression, and the variation due to the error, okay, due to the prediction yi. So this is square, this is square. So in fact, this is yi minus yi hat, but since this is squared, there's a no big deal. So SSC is yi minus yi hat squared. So it just uses, the ANOVA uses the model assumptions to devise tests about the model parameters and the goodness of fit. Okay. So, okay, we have SST is equal SSR plus SSC, equivalent to this one. Okay, we know SSC, we know that SSR is equal to this, and so on and so forth. Okay, we talk about this. So the total sum of squares, the regression sum of squares, and the error sum of squares. That's great. Let's again make a recap. So what is SSR minus SSC? SSR denotes how much of the variation in the y values can be explained by the regression model that we fit. Okay? And SSC shows the variability about the regression line, which is the unexplained, which is the random variation in the y values. Okay? So SSR, so in fact, this thing is very intuitive, or just makes a good, let's say, place in your head. So SSR is the explained, okay, source of variation, which is explained by your model, of course, and this is the unexplained error, okay? This is the unexplained error, or this is the random error, right? And this is the total error, right? That's great. Now, R square, so let's go back and talk about R square. R square, which is SSR divided by SST, that's equal to explained by the total error, right? So if explained over total is large, it means that you are able to explain the error in a very good way. So if R square is large, it means that the explained error is large. So that's fine, right? But otherwise, if R square is too small, it means that the explained error is very small and the unexplained, the random term is very high, which means, well, the model that you fit is not very good. Well, so this is the ANOVA table. Okay, so in generally, we just use the tables for ANOVA. So, so you have 5 columns here. This is the first column, C1. Okay. So C1 just shows you the source of the variation. So the first line, so the first part is the regression sum of squares, which is SSR, right? The second one is the SSC, the error sum of squares. And the last one is the SST, the total sum of squares. And okay, so the second column just give you the name, okay, SSR, SSC, SST. Sorry, so this just gives you the computed sum of squares. So what you do is you will just write the numbers here, right? And the second part, the third column just gives you the degrees of freedom. So the total degrees of freedom for SST, remember for SST, so remember the total variation, it is yi minus y bar. How you find the the sigma square, the estimator of sigma square, which is s square, when you don't have any model, you will divide it by n minus 1. So this is the degrees of freedom whenever you don't have any model. So this is, you just divide SSE by n minus 2. Remember why? Because you have a model and you have to fit 2 parameters. So this is n minus 2. So if you just sum them up, it should be equal to n minus 1. Hence, just 1 is left there. This is the regression sum of squares. And in the fourth column, you have the mean squares. Mean square, we mean the average squares, okay? So the average squares. The average squares per degrees of freedom. How we find them? What we do is we just divide SSR by 1, right? This is what we call an MSR, mean square regression. And we just divide SSE by n minus 2, right? This is SSE divided by n minus 2. This is what we call a mean square error. And it is also, remember, we just said that this is the estimate for the R square, estimate for the sigma square. This is the variance, the sample variance. Okay. And the last column, so you only have one thing here. It is the MSR. It is the MSR divided by MSE. Okay. So this is in fact, this is equal to the MSR divided by what? MSE, right? Or MSR, instead of MSE, you can just write the S squared as well. This is in fact, this is what we can call as the F observed, right? So in fact, this will give you the observed value of a F random variable, which represents an observed value of a hypothesis test. Then what is the hypothesis test here? Okay. The hypothesis test is, well, whether beta 1 is equal to 0 or not. Okay, so this is our hypothesis test. So if the hypothesis is true, which means if beta 1 is equal to 0, then, well, it turns out that SSR divided by sigma square and SSE divided by sigma square, they are chi-square random variables with 1 and n minus 2 degrees of freedom. And if you just take the ratios of two chi-square random variables, okay, which is SSR divided by 1, and SSE divided by n minus 2, so these are in fact, okay, SSE. So in fact, this is okay, so this part is in fact, let me just give me a second. Okay, so you can, well, we know that a chi-square random variable, let's say I have a chi-square random variable, call it, I don't know, M, we don't have M, right? M, let's say this is a chi-square random variable, and assume we just divide it by its degrees of freedom V of n, and divide it by another chi-square random variable n, which is divided by its degrees of freedom n. Then this is a f random variable with Vm and Vn degrees of freedom. Okay, so using this, you can just write, well, remember, SSR divided by sigma square is a chi-square random variable, right? SSR divided by sigma square. This is a chi-square random variable divided by its degrees of freedom, which is 1, divided by SSE divided by sigma square, divided by its degrees of freedom, which is n minus 2, okay? Sigma squares cancel. This is equal to MSR divided by MSE, and so this is a F random variable with 1 degrees of freedom, because this is a 1 degrees of freedom, 1 degree of freedom, and this has a n minus 2 degrees of freedom. Okay, so this is my F random variable. But so why do we need to make this test? Because we are already making this test in using t-test, right? So in t-test, we said that, well, b1 minus beta 1, in fact, instead of beta 1, we just write 0, divided by s of b1. Well, this is t-distributed, and we are just making the test there. Well, in simple linear regression, you're right. There's no difference between the Anova table or the F-test associated with Anova table and the t-test associated with v1. So when we will have the difference, if we in the next let's say chapter, when we are dealing with the multiple linear regression, there we will have several regression parameters like beta 1, beta 2, beta 3. Then the the hypothesis of the Anova table will be H0 beta 1 equal to beta 2 equal to beta 3 is equal to 0, versus at least one of them is not 0. Okay, so in simple linear regression, there is no difference between F or the Anova table and its associated test and the t-test, but in multiple linear regression, we will see that there will be a difference. Okay, so, well, this F ratio will be rejected if F is greater than the critical value of alpha with 1 and n minus 2 degrees of freedom. And we know what happens if H is rejected or not from the t-test before. Okay. Well, as I said, we just use a t-test for the same hypothesis, okay? And we use that just this thing, okay? T is equal to b1 divided by s of b1, which is s divided by root sxx. So what you can do is just take the square of this. So t is equal to t squared. So b1 squared divided by s squared is xx. So, okay, so b1 times sxx, that's equal to sxy, and this one is equal to SSR divided by S squared, and this is equal to, in fact, F value, okay? So F value is equal to, in fact, what? T squared, right? So the two-sided test for T squared, or the T observed value, the square of the T observed value for alpha over 2 with n minus 2 degrees of freedom is in fact equal to the F observed with alpha, okay, and with 1 degrees of freedom and n minus 2 degrees of freedom. You can also see it here. See, this is F, okay, this is the F observed, and this is what we have here, 18.03. And it turns out that, well, 18 squared, okay, is almost equal to 325. So of course, there's a round error there, but that's not a big deal. 18 squared is almost equal to 325. Okay. So this is what we see, right, in terms of Excel in the Anova table. You see, this is the first column, this is the second column. So there may be a change, that's not a big deal. So degrees of freedom is 1 here, n minus 2, you have 32 many observations, which is given here, right? 32 here, this is n minus 1, this is n minus 2, this is the sum of squares, this is the total sum of squares, right? This is the regression sum of squares, and this is the SSE random, this is the error sum of squares. Again, this is the controlled or the explained errors, this is the uncontrolled or unexplained errors. And this is the MS, okay, MSE. So this is the MSR, the average sum of regression sum of squares per degrees of freedom. This is this one is um, the MSE, which is the regression sum of squares again per degrees of freedom. And remember, what is this? This is the S squared, right? This is the S squared. So the square root of 10.43 is equal to, in fact, S, and it's also given here, okay, the standard error. See this? This is 3.23. This is equal to 3.23. And F value is this thing. Okay, let me just change the color so that you can see it. It is this thing, okay, divided by this thing, and it's equal to 325, which is a very, very large value, and the p value turns out almost 0. Okay? And again, this is the part, this was the part for the Excel, okay, and this is the part for R. Okay? So R just gives you, well, this is the, okay. So remember, this is table 1, this is table 3, sorry. And This is table 1. You see, this is the standard error, which is S81, 31 degrees of freedom. This is R squared. This is adjusted R squared. We will see what an adjusted R squared is in the next slides. And the F statistic is 325, and the p-value is less than 2.2 to the power 10, 2 times 10 to the power minus 16, which is almost zero, right? And this is related with the Anova. Okay. Okay, and you also have an Anova table in R. So as you see, it just gives you, it doesn't give you the total part, okay? It doesn't give you the total part, but it just gives you the regression sum of squares. As you see, this is 3,390. You see this? And then the residual sum of squares, it's here. Then the mean squares, and the F value, and the associated p-value there. Okay. So this is, again, this is from R. This is from R, and this is from Excel. Okay, so all of them give you the same results for the same problem. Let me just finally, you will see this in the recitation, but let me just give you how you just run the regression in R. So here I have the text, which is which you have the data there. Okay, so this is the data that I have. In the first column, you have the GPAs. This is the first data, second, third, and so on and so forth. And this is the data for the ALES. There are 33 many data there. So what I do is I just read the data using this thing. Okay, data is equal to read table. And then, well, we can just see the data $GPA. So this is the GPA of people. This is the ALES of people. And then what I do is I just run the linear model using this keyword. I say that just use ALES is your y variable and GPA is your x variable, because you have the left-hand side, you just write ALES, and the right-hand side, you just write GPA, and assign the results to the variable result. And then I say that, well, just summary the result, and this is the summary, okay? This is the summary that you have. This is the table that you see this, and these are the R squared, the adjusted R squared, and F values. You can also see the ANOVA, right? ANOVA result. If you just write this is the ANOVA for the ANOVA table for the results. Okay.